course not. Go ahead.
Okay, go. Okay. Hello and welcome to another amazing adventure of the New York City Category Theory Seminar. And we have the privilege of welcoming back David. I think this is like your 10th talk here, and every year, and it's almost, I think, except for COVID, whatever. David Ellerman, and he's going to talk about to interpret quantum mechanics, follow the math. Math of quantum mechanics equals linearized partition math. Anyways. And we have slides, and there's a link to the paper also. Anyways, David, take it away, please.
Okay. Thank you, Newsom. Prior to starting, we were just reminiscing, and I thought I would go back over some of the history of my talks. Most of my career, I got my PhD in mathematics under Rowett. I was Rowett's first PhD student, and but most of my career was spent in economics, and I eventually got so sick of the ideology in economics that at age 62 decided to go back into math and do it. It took a while to sort of retool my neurons to do mathematics again after doing something as synthetic as economics. And the way I oriented myself was that I'd written a paper a long time ago with Jean-Carlo Rota, and he died unexpectedly in 1999 at age 66. And those of us who had worked with him sort of split up his unfinished work, and I decided to try to extend his work on partitions, and so the lattice of partitions with join and meet was 19th century known to Schroeder and Dedekind, but to do a real logic of partitions, you have to at least have an implication operation. And that had not been done. No new operations on partitions had been done throughout the 20th century. So the key thing was to finally develop what was the correct notion of implication for partitions. And so then I developed the full logic of partitions. And category theory here is relevant because usually logic is identified with starting with propositional logic, which is really a special case, should be thought of in terms of the logic of subsets, Boolean logic of subsets. And partitions and subsets are categorically dual. The image and co-image, or the inverse image of a function is a partition, the image is a subset. And so that's a fundamental duality. So in a sense, the logic of partitions is dual to ordinary logic. And so then the question is, if it's the same sort of level of fundamentality as a mathematical theory, we all know what ordinary logic is, logic of reasoning. And so what is the logic of partitions good for, if it's so fundamental and in a sense dual to ordinary Boolean logic of subsets? So the first answer to that was the quantitative version of the Boolean logic of subsets is finite discrete probability theory, as you know, Boole's original book on laws of thought included both logic and probability theory. So what is the quantitative version of partition logic? Turned out to be the notion of entropy or information, logical entropy. And that turned out to lay new foundations for information theory, which laid the foundation for really Shannon entropy is not a measure, logical entropy is a measure, and on a set in the usual sense of measure theory. So one use of partition logic was to really develop the whole theory of information from the logical starting point, and that's now published in a book called New Foundations for Information Theory. And so then some point along the lines, I decided to try to learn quantum mechanics. And as I got more and more into quantum mechanics, I realized that basically the operations you're doing in the math of quantum mechanics are just partition-like operations, but redone in the vector space, in Hilbert space. And so that's what I've been developing the last couple of years, is this idea that the mathematics of quantum mechanics is really the linearization or the vector space version of partition mathematics. So if that's all works out, then you can say, well, the primary use of partition logic is not only to refound information theory, but to actually say what's going on at the quantum level in a very schematic form. So the talk is about the mathematics of quantum mechanics, not the physics. We're just taking the mathematical form and showing where that comes from. So all the questions about specific observables, position, momentum, spin, all that all comes out of quantizing classical physics. So I'm not talking about that. I'm just talking about the mathematical form. And so we'll see here that how we represent quantum states, how the notion of measurement in quantum theory, the von Neumann type 1, type 2 processes. And we'll see that the concepts that are really crucial are the notions of indefiniteness versus definiteness, or indistinguishability versus distinguishability. So that's the approach, is to show that this math is really just the restatement in Hilbert space of partition mathematics. And so partition mathematics gives you the sort of skeleton, the logical skeleton in that sense of quantum mathematics. And that's what I mean by following the math. I mean, that's obviously play on the expression, follow the money. You follow the money that somebody has, and you figure out maybe what's really going on. And the idea here is the same. Follow the math back to the basic concepts, and then you see how to literally interpret quantum mechanics. So in that sense, it gives you the interpretation. And this, I think the closest philosopher of physics that I can see among the many these days is Abner Shimony, the late Abner Shimony. And he was very clear that this notion of indefiniteness, objective indefiniteness, not just subjective or epistemological indefiniteness, but objective indefiniteness and the superposition principle. These are the basic concepts that just we can't make sense out of in terms of our usual common sense or even in classical physics. So quantity, which has an indefinite value, objectively indefinite, it's not just that it has a value, we don't know it, that sort of thing. And that conflicts with classical physics completely. So this is what Shimony called the literal interpretation of quantum mechanics. And this is interpretation resulting from the formalism, that is the math, quantum mechanics literally is giving representation of physical properties themselves rather than human knowledge of this, and taking this representation to be complete. And that separates it from a lot of the other principal ways in which quantum mechanics is interpreted, where you add something to it in the Bohmian mechanics or in spontaneous localization theories and so forth. So I give a few quotes here from physicists and philosophers. Steven Weinberg, particles neither definitely here nor there. And so you're juxtaposing here this notion to the pop sci notion that a particle can be in two places at once, which is nonsense, but it can be indefinite between two places. And so Weinberg is very careful to say it's not that it's both here and there, or that goes through both slits at once in a double slit experiment, but it's neither definitely here nor there, or spinning neither definitely clockwise nor counterclockwise. And a philosopher, Paul Feyerabend, said the same thing. So we're not trying to interpret it by saying that superposition means simultaneously in two definite states. Absurd. but trying to make sense out of the notion of objectively indefinite. And that's, of course, where partitions come in, because partitions are the natural mathematics to express indefiniteness and definiteness. So let's take a moment and look at the normal imagery, and the most misleading and actually malicious imagery for superposition is the study of the sum of two definite waves giving another definite wave, as in Fourier analysis. So this sort of picture here, and so one point I would make is that Schrodinger and perhaps others thought that the Schrodinger equation actually described a physical wave, and people still try to make sense out of that idea, and that has misled quantum mechanics interpretation for almost a century. I mean, if you think quantum mechanics was really solidified in 1925, well, that's just about a century ago, and so when Einstein said that the Lord is subtle but not malicious, I think that's being over optimistic. I think that people have been misled for a century by the idea that it's wave mechanics or that there's some sort of physical wave. And so I think God was being a little bit malicious in that sense. So I'm not saying the math is wrong. The complex numbers are used, I think, basically because they're algebraically complete extension of the reals, but the complex numbers are the natural mathematics in which to describe waves. So the math of the wave function and all that is not wrong. It's just the imagery that people attach onto that, as in sum of two waves is another definite wave, is wrong. So the interpretation one should give to quantum superposition is a state that's indefinite. This is like neither definitely here nor definitely there. And so you can say where the superposed states differ, it's indefinite and could be definite where they're the same. And so I give a little picture here. Here you have two triangles that where they are the same is on this vertical AA axis, but where they differ is on the labeling of the two equal sides, the isosceles triangles, or the opposite angles. So if you take a superposition of them, this is the way you should represent the superposition, as indefinite where they differ, but definite where they are the same, not as this idea that its superposition is both things at once, which is nonsense. So one way to get a hold of this is to realize that our classical physics and our common sense, evolutionarily given theater of our minds thinks in terms of three-dimensional space and time, and this is could be called the view of definite all the way down, and that's play upon the old joke about turtles all the way down. So the classical common sense view is that reality is definite all the way down. And so that's where Leibniz's identity of indiscernibles principle comes from, because if you have two things that are not identical, then you just dig a little deeper, go down, down, down until you find a predicate where they differ, and thus you discern them. So if they really are indiscernible, then they have to be identical on this classical point of view. Now, so we're going to say this is exactly where quantum mechanics differs. That quantum mechanics isn't definite, reality isn't definite all the way down at the quantum level, and it gets to a certain point, and then any remaining indefiniteness is objective. And to carry out this program, you need to realize that there are all sorts of mathematical formulations of quantum mechanics. It's a beautiful mathematical theory, and so this article a number of years ago gave 9 formulations that were in the end equivalent. And so you got to sort of get the right formulation to then really see through what's really going on. And so I'm going to give what seems to me to be the right mathematical formulation in order to see where it comes from. They're all equivalent mathematically to do physics. That's well known. So the underlying concept to describe indefiniteness is the notion of a partition, and equivalently what Rota would call a cryptomorphic thing is an equivalence relation or a quotient set. So we have subsets dual to quotient sets, or subsets dual to partitions, and so forth. So partition pi on a set, and I'll keep it finite here and in larger than 2 to avoid trivialities, is a set of subsets called the blocks, or some people call them the cells, and they're disjoint, and their union is all of U, all of the universe set U.
Blocks are not empty, right?
Yes. The blocks are non-empty. I should say that, and so the thing we want to pull out of this partition is the difference between the pairs of elements that are in the same block and pairs of elements that are distinguished. So a partition distinguishes by saying all the pairs of elements in different blocks are distinguished by the partition. If they're in the same block, they're not distinguished by the partition. So the indistinctions, and this is where superposition comes in, inside a block. So the indistinctions of pi is just the union of all the blocks times themselves. And then the difference, the distinction set, did set, all the pairs U cross U that are not in the same block is the did set. So these are two fundamental notions that we'll see a bit more of them later on. And although partition logic has the join and meet, the two lattice operations, as well as the implication operation and a Schaefer stroke and a bunch of others, the basic operation is the notion of the join. And so if you've got two different partitions, pi and sigma, and the join is the partition where the blocks are the non-empty intersections. So there may be a lot of course, the blocks in B cannot intersect each other, and similarly for sigma, but they can intersect each other. And so that forms another partition. So this is, all the points that are common to these two blocks. So that's the basic operation we're going to pull out of partition logic. And we're going to see that this is actually the logical form of measurement in quantum mechanics, projective measurement, but that's the story down the road a bit. So let's take a look at the Hasse diagram for a lattice of partitions and think of it as skeletal form of the possible states of a particle. And the partition, you can take the points in the partition as being equal probable, or you can take them as having point probabilities. So here we're thinking of partition with probabilities assigned to the points, so you got P1 through Pn. And so a partition is the skeletal form of a mixed state of a particle. In here, I'm assuming you know what a mixed state is in quantum mechanics versus a pure state. A non-singleton block is a superposition state. So the elements in a block are considered to be superposed. So this is the skeletal form of what you have in quantum mechanics, where of course the states that are superposed have scalar coefficients. You get all linear combinations, blah blah blah. So you wipe out all that, you just get the skeleton, and that's a non-singleton block in a partition. So this would be an example such a block, and I usually use a shorthand ABC rather than the brackets. So you get a picture like this. So this is the whole lattice, and at the top you get where all there's no superposition, that everything has been distinguished from each other, and that's called the discrete partition. That's the most refined partition at the top. And at the other end is a pure state where they're all in one block. You have only one block, and that's called the indiscrete partition. And then everything in between are mixed states, but they're non-classical mixed states because each one in between has a non-singleton block, and some of them have two non-singleton blocks. So, so this, as it were, is the quantum world, and the classical world is this little thing at the top where everything is distinguished from each other. And accordingly, you can reformulate Leibniz's principle, the law of identity of indistinguishables. So suppose you have two elements from a universe set, U and U prime, they're in the indent set of pi, then they are equal holds if and only if pi is the discrete partition. So everything that can be distinguished from everything else is distinguished in the discrete partition up here, and that's the classical world. And so the only indistinctions here are the self pairs, are the diagonal elements from U across U. And so this holds there. If U and U prime are in the indent set of the discrete partition, which is symbolized like this, then they're equal because it has only the self pairs. But once you start getting non-singleton blocks, then you get different things being not distinguished. So the Leibniz's principle in this form doesn't hold unless pi is here. So you get a direct translation of the Leibniz's principle into the lattice of partitions when they act classically, namely when everything is distinguished from everything else, so that there's no indistinctions, non-trivial indistinctions, which are called superpositions. Now, so let's now talk about how to represent. See, there's the two main concepts we have to deal with in quantum mechanics are the notion of states and observables. Those are the two main tools. And so it turns out that both states and observables reduce down to partitions in skeletal form. So let's start with the notion of states. So what is the way to represent states in quantum mechanics that makes this clear? And that turns out to be not the wave function representation, but the density matrix representation. And they're both equivalent mathematically, but the density matrix one is the one that really shows you what's going on. So let's take this partition here where A, B, and C are in the same block and D is a singleton. Then if you do a incidence matrix for that as an equivalence relation, this is the incidence matrix. So you got A, B, and C all have ones. They're all in the equivalence relation as a set of ordered pairs, and D is also in there, but all the other combinations are zeros. So this is incident matrix like this of an equivalence relation is a rudimentary form of a density matrix because you just need to normalize it. You have a density matrix, and here it is. If we assume the four elements, four states of a particle are equal probable, then you have this density matrix here, and you see you have the diagonal elements which have to sum to 1, which are the point probabilities, and then every off-diagonal element, the non-zero off-diagonal elements in the density matrix are the indistinctions of the partition, and they're what are called in quantum mechanics the coherences. And these coherences are the source of all the weird interference effects in quantum mechanics, in the two-slit experiment and in the other ones. And the zero entries here are the distinctions. So this density matrix row of this partition is just the way to represent an equivalence relation. And in more general density matrices, you can represent any quantum state. And that's why this is the way to represent quantum states in order to see that really the underlying mathematical notion back at the logical level or the skeletal level is a partition or equivalence relation in this case.
I have a question. So here, the 1, 4, 1, 4, 1, 4 are all equal, but could it be possible that you have A, B, C indistinguishable, but A is a bigger shot and B and C are smaller, or no?
Yeah, you can have any point probabilities you want. It's just
Okay, got it.
Yeah. Just so the diagonal has to be the probabilities, has to add to 1. Now, so that's how you represent states. And then the question is, okay, so this is a state that is definite, that A, B, and C are distinguished from D, but A, B, and C are not distinguished from each other. So how do you go from that indefinite state to something that's more distinguished, where you make distinctions? In other words, you put in some more zeros here, make distinctions, and that's, of course, what happens in quantum measurement. And the point here is that the skeletal form of projective measurement is just the join operation. So let's illustrate that here. Here's the partition, the equivalence relation represent here. And so let's now join it with this one here, where AC is not distinguished and BD is not distinguished. So we're going to take their join, which is just this here, if you think it through. But, and here it is in the picture, the two things being joined in the Hasse diagram to give you that. So what is the quantum mechanical version in the full math of quantum mechanics of this partition join operation? And it is projective measurement as described by the Luther's mixture operations. So you're representing states, and we'll see later you represent observables also by partitions. And when you bring those two partitions together to measure the state by the observable, those two partitions combined by the join operation, and the full version of that in quantum mechanics is what's called the Luther's mixture operation. And that goes back to a paper by Gerhard Lüders in 1951, where he really characterized this projective measurement in these terms. So let's go through the Luther's mixture operation. We're going to join this partition onto this partition. And to do that, we need to, this partition here is like representing the observable, and this is representing the state. So we're going to measure the state by this observable. So for Luther's mixture, you need the projection matrices corresponding to the eigenvalues, as it were, in the observable. So here's A and C, you've got a 1 in A and a 1 in C, and here's B and D. And then the Luther's operation, it pre and post multiplies the density matrix that we start with by these two projections and adds up the result. So here we're starting, here's our starting matrix, and we're going to pre-multiply and post-multiply by the projection AC. We get this thing here. Then we do the same with the other projection. Here's the BD projection. We get this thing here. We add these two together, and we get this. So this is the post-measurement density matrix by the Luther's mixture operation. And look at it, it is exactly the density matrix of what is the join of these two partitions. You see that A and C are still together because you have an off-diagonal element here that says they're cohere together. They haven't been decohered. But B has been decohered now because B was separated when you took this join. So B now has zeros in its column and row, and D always did have zeros in its column. So those two are singletons, but A and C are still in coherent superposition, and that's exactly what this partition says. So the partition join operation we see here is just the sort of partition version of the Luther's mixture operation, which is the way to describe the way in which a density matrix transforms under projective measurement. But if you don't see, if you don't look at the projective measurement operation as in terms of density matrices or the Luther treatment of it, you won't see this connection to partitions. So you've got to see the quantum theory math in the right way to see where it's all coming from down at the logical level. Okay, so that's the treatment of density matrix. Now let's go to observables. Remember, we have two states, two things we have to account for. The states and observables are the two main mathematical tools in quantum mechanics we just treated states in terms of density matrices. So let's move to observables. And here there is a what I call the yoga of linearization, a semi-algorithmic procedure. It's in the mathematical folklore. I don't know anywhere where they really treat it rigorously, but here's how it goes. So in this case, you don't attach, you can start with partitions if you want, but you don't attach probabilities to the points. And the yoga transforms a set concept into a vector space concept. And the way the yoga works is you take the set, the underlying set, U, you take it as a basis set for a vector space, and then you apply the set concept to a basis set, and you see what it generates. And what it generates is the corresponding vector space concept. And that's the yoga. So you start with the universe set. Well, that you, by definition, take that as a basis set. So the subset, the square brackets here just mean generated over some field K. The cardinality of the subset, the corresponding vector space notion to cardinality is dimension. This is all, well-known mathematical folklore. Subset goes to subspace, obvious. And it gets a little more interesting when you then say, okay, let's now take a numerical attribute. So, logic, you have attributes which apply or don't apply, but a numerical attribute, something like weight or height or age, where you assign numbers to things in the underlying field. So you start with this sort of set notion, a numerical attribute assigning values to the elements of U, and then the corresponding vector space concept is where you define a linear operator on the vector space by this thing here. So U is remember the little u's are from this basis set. The operator is defined by just f of U times U. So now you define the operator on a basis set and you extend it linearly to the whole set. Here's the set notion that says this function restricted to a subset S equals some element, some scalar from K times S. So this is like an equation that says for a subset, some subsets and some scalars K, this holds. Well, that's just the eigenvalue equation in the vector space. That this is the equation for an eigenvector and an eigenvalue. So what would be the set notion of an eigenvector? It's just a constant set. It's a set where every point in S is assigned the value K here by F. That's the corresponding thing to an eigenvector. So these are set concept and vector space concept. The value K, of course, is the eigenvalue. When the special form here is a characteristic function, well, what does a characteristic function define? Well, it defines an operator, which applied to U is just a characteristic function, U times this, and that's a projection operator because the eigenvalues are 0 and 1, and those are the way you define a projection operator. And then you have fundamental thing that the original operator can be, has a spectral decomposition of the sum of the eigenvalues times these projections. Projection here down to the subspace generated by the eigen vectors for that eigenvalue. And here is the set version of spectral decomposition, that F itself is decomposed into K times the characteristic function. So you feed in a value little u here, it gets a 0, 1. And if it gets a 1 for u that's in F inverse of K, then you multiply times K. Otherwise it gets a 0. You add it up over all the small k scalars in the image of F, and you get F. So spectral decomposition of linear operators corresponds to this sort of spectral decomposition of set functions. So you're getting a whole dictionary here to translate between set concepts and vector space concepts, and that's the yoga of linearization. The set of constant sets is just the power set of ones that have K, and that's corresponds over here to the eigenspace of K eigenvectors, VK. That's where this projection goes to this eigenspace. And if you have another function on K, on U into K, you can define just the way you did up here, another linear operator, and then the idea that F and G are defined on the same set U turns out to mean that the F and G have U as simultaneous eigenvectors. As you see the way they're defined, the U's are all eigenvectors, so they have a base of simultaneous eigenvectors, and we'll see that's a very important notion to remember. So what is the observable notion that corresponds to a partition without probabilities, just the inverse image of a numerical attribute, that F inverse partition? And that turns out to be a direct sum decomposition of the vector space. So remember, the yoga was that you apply the set concept. So apply this set partition to U, and what does it generate? Well, each one of these generates that subspace V of K here, and those subspaces are disjoint in the sense they only intersect in the zero vector, and they form a direct sum decomposition. So the notion of a direct sum decomposition of a vector space is the correlate or the vector space version of a partition without probabilities. And of course, this direct sum decomposition is exactly what you get as the eigenspaces of a observable. So what's important in observable is not so much the exact numerical values, but where eigenvalues are, where they're the same and where they differ. All that information is preserved in the eigenspaces, which form a direct sum decomposition. And so the set concept here is the corresponding vector space concept. So the disjoint union of these is the whole space, and the direct sum of all these is the whole space. So that's how that works. And I could add on here, what about the Cartesian product of two sets? Well, when you take two basis sets for the vector space and you take their Cartesian product, you get ordered pairs. So what does that linearly generate? In this case, bilinearly generate. It generates the tensor product. So category theory misleads you a little bit here, because the proper notion of product for vector spaces to do quantum mechanics is not the direct product, categorical direct product of vector spaces, but the tensor product. So the tensor product is the one that's generated by the Cartesian product of the two basis sets. Of course, where you're right, U, the ordered pair, U prime as U tensor U prime. And that is the basis set for the tensor product. Okay, so now let's start to, we have these two ways in which we translated the two concepts of basic concepts of states and observables, both back into partition math to see where they come from. So let's now go over some of the peculiar aspects in quantum mechanics math and see how it all plays out at the partition level. So one, what was originally thought to be a big deal, characteristic of quantum math is that the observables can be non-commuting, and which doesn't happen in classical physics, and even conjugate observables. And when you look at linear operators that commute or don't commute, or conjugate, that seems to have nothing to do with partitions. So let's see how it really does have to do with partitions. So we've got two self-adjoint operators here on the vector space, and we've got two direct sum decompositions, DSDs of their eigenspaces, this one for F and this one for G. And what we know to do is to take their join, or take their join like. So let's take all the intersections of these eigenspaces from each operator and take all the non-zero, and they all intersect, of course, in the zero vector, but the ones that this is analogous to the non-empty intersections in the case of a set join of two set partitions. So let's do the same operation for these direct sum decompositions of eigenspaces. And of course, the vectors that are in here are by definition simultaneous eigenvectors because they're in both the eigenspace of F and an eigenspace of G here. So what is different here now is that unlike the case of partitions on the same set, all these subspaces here don't have to span the whole space. That's the trick. And so let's call the space they do span SE, because they're all the non-zero subspaces spanned by the simultaneous eigenvectors. So there's our space which may or may not be the whole space. Now let's look at the commutator of F and G. So that's defined this way, and that's a linear operator on the space. So it has a kernel, and the kernel is a subspace of all vectors such that the commutator times it is zero. And the theorem is that this simultaneous eigenvector space is the kernel of the commutator. And it's, of course, proven in the book form or in the paper. So here we have, what do you mean when you say these two operators commute? It means the commutator is zero. So that means the kernel is the whole space. So that means that the simultaneous eigenvector space is the whole space. So now we've defined commuting solely in terms of this join-like operation on the direct sum decompositions, which are the vector space version of a partition. So it's just a partition join again, and gives us, if they don't commute, it means the simultaneous space doesn't span the whole space, and it could even be zero. There could be no simultaneous eigenvectors, and that's when we say they're conjugate. So the whole notions of commuting, non-commuting, and conjugate all boil down to what happens to, you take the partition-like join of these join-like operation on these direct sum decompositions and see what it spans. So that's what started out looking like it had nothing to do with partitions. It turns out to be all about partitions. And in fact, it's all about the direct sum decompositions, not the full operators. The values of the operators don't make any difference to whether they commute or not. It's a property of the direct sum decompositions of the two eigenspaces, where they join to give you the whole space or not. And of course, when you look at the Heisenberg so-called uncertainty principle, you should really call it, uncertainty speaks about subjective uncertainty. You should really call it the indeterminacy principle or the indefinite principle. And so position momentum are the classical examples of conjugate observables. And you go through all this math and so forth, but what it really boils down to is that you cannot have a precise measurement of position and momentum at the same time. And what does that mean? That means there's no simultaneous eigenvectors. In other words, the eigenvector space is zero. So this is really where it all boils down to. So in the set case, we have just these numerical attributes, and if they're defined in the same set, we call them compatible. And if they're the vector space version, we call them commuting. So now this join-like operation, Hermann Weyl is really, I'll give a number of quotes from him. He really understood all this pretty well. And he says, he calls a partition in the set sense or a partition in the vector space sense, namely just direct sum decomposition. He calls it a grating, like a cheese grating or something. And he says that the combination of two gratings presupposes commutativity, and so it does. That if the two direct sum decompositions you take the join, it doesn't span the whole space. You don't have a join operation. You've got some kind of pseudo join or proto join. So if you really want to combine them, then you have to presuppose commutability. So that was in Weyl. So another point here is that now we're comparing these numerical attributes defined on the same set and community observables in the quantum case, and if you have a complete set of compatible attributes in the set case, it means their join is a discrete partition. It means that those attributes distinguish everything, and in the quantum case, that's called a complete set of community observables or operators, going back to Dirac, and it's the same thing. That's the maximum bit of distinctions that you can make. Anything beyond that is objective indefiniteness. You cannot distinguish any further than a Cisco, and so it's not distinctions all the way down. Becomes very obvious. So now that's the treatment of commuting and non-commuting and conjugate observables in terms of partitions and the vector space version of partitions. So let's now go to indistinguishability. So here I put two corresponding things. So here we're talking about numerical attributes, a set of compatible ones. On the same set, they're said to be complete if their join is a discrete partition, which is all singletons, so everything is distinguished from everything else. And the blocks are cardinality 1. Each element of U would then be characterized by an ordered set of attributes. So if you have a complete set of attributes, then each element is going to get for each one of those some value. And so you can characterize each element then uniquely by an ordered set of attribute values. And that's all at the set level. And you apply the yoga, you see that's all true at the quantum level. A set of commuting observables, a commuting now so that you can take their join, is complete if their join of their DSDs, just like here, join of their partitions, is the DSD where all the eigenspaces are of dimension 1 instead of cardinality 1. Remember, cardinality and dimension are correlated by the yoga. Then each of the simultaneous eigenvectors is uniquely characterized by its ordered set of eigenvalues. And that's the well-known way in which Dirac used the Ciscos here to characterize the eigenvalues by just the complete ordered set of the states or eigenvectors by the ordered set of eigenvalues from a Cisco. So the very fact that this is a maximal description, you can't further specify, implies that we're not dealing with distinctions all the way down. So this is a way to intuitively think about quantum level reality is not definite all the way down. It gets down to a certain point and that's it. And of course, that's probably related to Planck's constant. Whereas in the classical case where Planck's constant is 0, it's definite all the way down. So as Sakuri says, quantum mechanics identical particles are truly indistinguishable. This is because we cannot specify more than a complete set of commutative observables, a Cisco, for each particle. In particular, we cannot label a particle by coloring it blue or whatever. We cannot sort of start adding on other properties. So this by itself tells us that we have to have objective indefiniteness. We don't have definiteness all the way down. That alone. Now, in the paper and in the book, underlying book, I went ahead and derived the bosonic and fermionic spaces, the dimension of the spaces and the quantum statistics and all that. But that's too much here. So let's move on. Let's now look at the two von Neumann processes. You know, von Neumann had these type 1 and type 2 processes. And a big piece of quantum mathematics is a Schrodinger equation, the time-dependent Schrodinger equation that describes the evolution. And that doesn't seem to have anything to do with partitions. So what the hell am I doing here? The Schrodinger equation doesn't mention partitions at all. So let's approach it this way. Let's take von Neumann's two types of things And von Neumann said that the type 1 process was measurements. And we've just seen before that measurements described by the Luther's mixture operation make distinctions. That's what partition join does. It combines the distinctions of two partitions, and similarly in the vector space version. So type 2 process is evolution of an isolated systems described by the Schrödinger equation. So what would be a natural characterization of type 2 process to distinguish it from type 1 process? Well, type 1 process makes distinctions. That's what joining partitions together or making a measurement actually does. And so the natural characterization of type 2 processes would be ones that do not create distinctions. Very simple. Create distinctions, don't create distinctions. Is that true? Well, how do you tell whether two quantum states are distinguished or not? Well, the extent to which they are indistinct or distinct is given by their inner product. So the natural characterization of the processes that are not changing the indistinctness or distinctness between states would be a process that preserves inner products. And that, of course, is the unitary transformation, the definition. And that indeed is a correct characterization of type 2 processes. So we see that the type 1 and type 2 processes are distinguished, analyzed in terms of our fundamental notions of distinctions or not. Type 1 make distinctions, measurements. Type 2 don't make distinctions. And the extent to which two states are distinguished is given by their inner product. So the type 2 processes are correctly characterized by transformations that preserve inner products, and those are called unitary transformations. So here's our skeletal form of what's going on here. We saw previously that measurement is taking the join of two partitions, one representing the state being measured, density function, the other representing the observable. And then unitary evolution transforms a orthonormal basis into an orthonormal basis. So if you start with the basis, your set, remember interpreting that as a basis set for vector space, then unitary evolution just maps it over into a different basis set, in this case, U prime. So this is sort of the skeletal version of type 1 and type 2 processes. And when I say skeletal, of course, all the scalars have gone out. You're looking at the underlying logical structure of these two things. Now, let's not forget about the Schrödinger equation. What's the connection? Well, that's Stone's theorem. Stone's theorem says there's a one-to-one correspondence with strongly continuous one parameter unitary groups and self-adjoint operators on Hilbert spaces such that the unitary thing is represented by this, and this is the form of the solutions of the Schrödinger equation. So the Schrödinger equation is the right equation to give you these unitary operators, and those are the ones that preserve the distinctions between quantum states. So we've now handled, in our partition analysis, the two types of von Neumann, type 1 and type 2 processes, and shown what's really going on in the Schrödinger equation. Okay, let's go to another topic, measurement and the collapse hypothesis. What's going on there? And there are all sorts of theories out there as to what's going on in collapse when you do a measurement and the superposition turns into one of the superposed eigenstates in a non-degenerate measurement. What makes it a measurement? And you've got analyses that it has to do with the interaction of a microsystem with a macro system, and then that makes macro systems something that has to figure into quantum mechanics, and there's what John Bell called a shifty split between micro and macro. And my point is that has all been undercut by Richard Feynman, dating back to his paper on quantum probability in 1951, And he makes this point that the crucial thing about measurement is distinguishability. And that's what separates measurement from non-measurement unitary evolution. So this is a quote from his later lectures, volume 3 on quantum mechanics. If we could in principle, so he's not talking about human beings observing some macroscopic meter or thing. He's saying, if we could in principle distinguish the alternative final states, even though you don't do so, the total final probability is obtained by calculating the probability for each state, not the amplitude, and adding them together. So that's when you can distinguish them. That means it constitutes a measurement. That's what measurements do, is distinguish things. If you cannot distinguish the final states, even in principle, then the amplitudes must be summed before taking the absolute square to get the probability. So Feynman all along analyzed measurement and non-measurement in terms of distinguishability. And he even, this bypasses the whole tortured literature about measurement involving the shifty split between macro and micro and the Zech-Zurich decoherence and all that which is kind of funny because, see, Feynman made this joke about philosophers of physics. He says that physicists need philosophers of physics the way birds need ornithologists. And so in other words, birds apparently don't. But yet Feynman himself actually gave examples that blow some philosophical views out of the water. And for example, in that same volume 3, he gives an example of a measurement at the quantum level. There's no macroscopic thing involved at all. And so the example, we give several examples, but one of them, easiest one to see, is you have a particle scattering off the atoms in a crystal. And the question is whether you should treat that as a superposition of scattering off of different atoms or as a mixture of scattering off of particular atoms. And that hinges on, as he points out, on the question of distinguishability. No macroscopic thing. This is all atomic level crystals. So if there's no way to distinguish which atom the particle scattered off of, then no measurement takes place. There's been no distinction. And so you add amplitudes before you compute the probability. But if say he says, for example, if all the atoms had spin up and scattering off an atom reverse the spin, then a distinction is made. There's a distinction as to which atom the particle scattered off of. And so then a measurement takes place, and then you have to add for each of those atoms those probabilities to get the final probability, and getting from some point A before the scattering to some point B after the scattering. So Feynman gave examples that just undercut the whole silly literature about macro and micro, and said the key concept is distinguishability. That's distinguishability is what separates measurement from non-measurement. So the principle here, this is sort of the principle behind it. You have an interaction, you have a quantum level system goes into an interaction, and the system going into the interaction is a superposition of certain eigenstates. If the interaction distinguishes, like those atoms distinguishing which one it bounced off of by having its spin flipped, then a distinction is made. In other words, a measurement is made, and it will then collapse to one of those atoms. And you can compute the probabilities by adding the probabilities. So he answered a question. You've got this whole literature that ignores distinguishability. And Feynman answered this back in '51 and repeated it again and again and again. But he didn't like to write directly to philosophers, and philosophers have to read him and understand. So here's a quote from a recent book by Travis Norson. It seems unbelievable. There's a fundamental distinction between measurement and non-measurement processes. This is von Neumann's type 1, type 2. Somehow the true fundamental theory should treat all processes in a consistent, uniform way. Well, that fundamental distinction, as Feynman pointed out, is whether the interaction distinguishes the eigenspaces in the superposition, or they go through the interaction without being distinguished, in which case no measurement takes place. So here is sort of a picture, image of a measurement. So you have this indefinite state, this is your superposition, and it's hitting a sieve or grating and in various different shapes. So it eventually, after the measurement, it has to go through one of these, and it will then acquire that specific shapes. Think of this as a piece of dough going through a grating of different types of pasta or something, and acquiring that shape. So that's sort of a very nice image. And that image of measurement as going through a sieve or grating is not new. It was used by Eddington, who said in Einstein's theory of relativity, the observer is a man sets out in quest of truth armed with a measuring rod. In quantum theory, he sets out armed with a sieve. And so this sieve, of course, is just the blocks. And so Hermann Weyl picked up on this in his philosophy of mathematics and natural science. And this is all in one of the appendices in Weyl's book. So he quotes Weyl, and then, he quotes Eddington and picks up on the sieve thing, which he calls a grating. And then he uses, in effect, this yoga of linearization, which I said is part of the mathematical folklore. And he used both set partitions and vector space partitions, in other words, direct sum decompositions, as the two types of gratings. So he starts out with a numerical attribute on a set, which defines a set partition or grating. These are these different states. And then he moved to the quantum case, where the universe set here, or aggregate of n states, has to be replaced by an n-dimensional Euclidean vector space. So he's moving up from the set concept of an aggregate of n states to a vector space. And he's using Euclidean here, I think, in the older sense, which we would now call inner product space. Not the way Euclidean is used these days, just the way we don't call sets aggregates anymore either. And then he goes on. The notion of a vector space partition or grating is a splitting of the total vector space into mutually orthogonal subspaces. So that each vector splits into these are component vectors lying in the several subspaces. And that's exactly the definition of a direct sum decomposition. So it's all there in Weyl, this going from a set partition to a vector space partition, which is a direct sum decomposition. So, one way to define a direct sum decomposition of a vector space is every vector in the space is uniquely represented by a sum of non-zero vectors from the subspaces. Then the subspaces make up a direct sum decomposition. So after referring to partition and a direct sum decomposition as a gradient sieve, he then notes that measurement means applying the sieve or grating, and that's exactly what we saw. That this making distinctions by this join-like operation described by the Luther's mixture operation. So this is all in this appendix to Weyl's book, spelled out rather nicely. So I'm now covered a bunch of things from quantum math. There's more in the paper and there's more in the book, but I don't want to try to cover everything now. So we've covered projective measurement, the Luther's mixture operation. We've covered commuting, non-commuting, and conjugate observables. We've covered indistinguishability. We've covered evolution by the Schrödinger equation, measurement, and the collapse hypothesis. And we could also, in some cases, the relevant quantum math really hasn't been developed. And that's the notion of logical entropy that I mentioned before, the quantitative version of partitions, which by the yoga directly generates a corresponding vector space or quantum notion, quantum logical entropy, and it directly measures information as distinctions, and you can precisely show the change in logical entropy when you do a measurement, and as you might expect, the Luther's mixture operation shows you the changes in the density matrix. So it turns certain coherences, certain non-zero off-diagonal elements in the density matrix into zeros. So it decoheres those coherences. And if you take all the compare these two density matrices before and after, and look at all the non-zero off-diagonal elements that got zeroed, in other words, decohered, take their absolute squares and add them up. That is the change in logical entropy. So the logical entropy directly measures measurement. It tells you the changes that take place in measurement. And the usual notion of entropy in quantum mechanics, namely von Neumann entropy, doesn't do that. Von Neumann entropy always increases under projected measurement, but you can't directly compute it from the change from the coherences that decohere, the non-zero off-diagonal terms that become zeroed when you do the projected measurement. So we systematically constructed at the set level this highly schematic model using set partitions, and so it's sort of like a skeletal model of what's going on in quantum theory math is this mathematics of partitions, set levels. The set partitions are behind both the main tools, both the states and observables, but set partitions with different additional structures. So if a set partition has point probabilities, that prefigures, in other words, gives you the density matrices, or if the set partition is inverse image of a real valued numerical attribute, then it prefigures, in other words, defines by the yoga self-adjoint operator or Hermitian operator as observables. The join of set partitions prefigures projected measurement, where the state represented by the density matrix is measured by the observables. So the two uses of partitions come together there in the join operation. And we've also seen that the isomorphic transformation from one universe to another at the set level prefigures this unitary evolution. And we've also seen how you can take the join of partitions on the same set and keep going until you get a complete set, and then the blocks are cardinality 1, in other words, discrete partition. And that prefigures the notion of a Cisco, where you take the join of commuting operators where the subspaces in the end are of dimension 1. In other words, it completely allows you to characterize all the one-dimensional eigenspaces. So moving to the end here, I'm claiming all this is not an accident, not a coincidence, that quantum math really tells us about this unintuitive reality of objective indefiniteness that quantum theory we know so successfully describes. So we're saying, how to literally interpret quantum mechanics? It's in terms of this objective indefiniteness. We've seen that the mathematics of quantum mechanics, looked at the right way, is just the Hilbert space version of the partition math, and partition math is a way to describe indefiniteness and definiteness. And thus, this follow the math approach leads to this literal or objective indefiniteness interpretation of quantum mechanics without other variables. In other words, unlike Bohmian, other equations, unlike spontaneous localization, not to mention many otherworldly ideas. So in the end here, I just put in a bunch of, here's the comparison table of the skeletal partition level concepts for states and the corresponding quantum level for states. So like a non-singleton block in a partition is a superposition, pure state. The indiscrete partition at the bottom is the largest pure state. A singleton block is like a classical state, so there's no superposition. It's only a single element, discrete partition, and so forth all the way down. It's also interesting that density matrices they are Hermitian operators themselves. They have eigenvalues, and the eigenvalues are all non-negative, and they sum to 1. So it looks like a probability distribution, And the literature basically doesn't take it seriously. You won't find it hardly anywhere where they actually try to interpret the eigenvalues of an arbitrary density matrix. And what we see here is that the eigenvalues of these special ones, density matrices formed from partitions, are just the block probabilities. The block probabilities, and so if we start with remember the pure state, this is this is the indiscrete partition, the one at the bottom. That's the pure state. There's only one block, and it has probability 1. Well, what's the eigenvalue of a pure state density matrix? It's eigenvalue 1, and then at the other extreme you've got the equiprobable here, and at the other extreme here you have the density matrix, which is just 1 over n times the identity matrix. That's the maximally decomposed classical mixture, and the eigenvalues in both cases are 1 over n, and those are the block probabilities in the discrete partition, and so forth. So that's a comparison chart for states, and we have another comparison chart for observables, which I won't go over in any detail. I mentioned it before. Here you have direct product going to tensor product. Ordered pair of elements in the direct product are the basis elements written this way for the tensor product. And then you have your analysis of commuting, non-commuting, and so forth. And finally, my last slide here. This is sort of pictures of the skeletal model at the set level of quantum mechanics. Your classical world is up here, where everything is distinguished, and the partition logic version of Leibniz's principle, identity of indistinguishables, holds there. It doesn't hold in any of these other places. And this is the quantum world, where you have superpositions, and then you have the 2 types of processes, measurement and unitary evolution, all illustrated at the set level in terms of partition math. So the claim is this really says what's going on. In the reason why we cannot spend a century being misled by the wave mechanics idea, thinking that it's some kind of physical wave, and what's really going on is that quantum mathematics is describing this reality of objective indefiniteness and objective chance, not just subjective chance and objective jumps. In the case of the collapse hypothesis, there's no continuous trajectory from one to the other, because that whole idea of a continuous trajectory comes from the idea of the principal continuity, also in Leibniz, of reality being definite all the way down. So that's my last slide. I thank you for listening.
Well, thank you very much. I think we all have to thank the speaker. I have a question, but anybody else have a question first? I love the beginning, the triangle you had in the beginning about capital A and small a on the bottom, capital A, and it's neither here nor there, all the way in the beginning.
Right.
Okay, there. Okay, but can you go from there and explain the double slit experiment? I mean, the double slit experiment is, 2 things cancel each other out. So how does indeterminacy cancel each other out?
Well, the key insight in double slit is that the particle is in a superposition of going through both one slit and the other slit. And if you make a distinction, then it breaks that superposition, and thus you get all the interference effects going away. And we normally think in terms of our mental models that it has to go through one slit or the other to get to the other side. That means that we're automatically assuming we have to go to full definiteness, where you have distinguished it in order to get to the other side. And the point is, at quantum level, it's the superposition that evolves, not the discrete version of it where you've already distinguished between the two states, slit 1 and slit 2, in the superposition. And we just don't have the mental equipment to, to think of that. So we think, well, to get to the other side, it has to go through one slit or the other. No, it's not. Unless you measure, of course, then it does go through one. You make a distinction then. So if no distinction is made, then the superposition evolves, and that's the key thing. And then you get all the interference effects coming in. And you can do a nice little diagram, just like a partition where you have two slits, and the bottom is where they're superposed, and the top is where they're distinguished. And we always think, well, you've got to go to the top level, the classical level, and to get to the other side, you got to go through one slit or the other. No, it's the pure state, the superposition, the two that evolves. And that's just unintuitive for our notions. But if you think of it in terms of partitions, it's the evolution of the superposition of going through slit 1 and slit 2. I have a little diagram in the book, but
so I mean, there is some canceling out here.
Well, that comes in the after it goes through, then you get the evolution, and that's where your cancellation comes in to give you your interference effects, which you won't get if you distinguish first, because there's no cross terms. The off diagonal elements, the density matrices, are called coherences because they represent the cross terms when superposition evolves. And so if you make the distinction, you're canceling out all those cross terms, you're decohering all those coherences, and to force it to go through one or the other. And when you don't do that, you don't make a distinction, then they continue to evolve and those cross terms cancel out or reinforce. So the point here is that the wave mathematics is correct because complex numbers or vector space over complex numbers is a natural mathematics in which to describe waves. And that has misled quantum theorists for a century, that the image should not be adding waves to get another definite wave, but this sort of taking some sort of a indefinite thing in between the two definite states, and then making a distinction eventually one way or the other when you do a measurement. So you have to retool the imagery of the wave imagery is that's where the Lord is being malicious, I'm afraid.
One more question. Feynman is before Zurich and the decoherence. So what was Feynman arguing against exactly? I mean, he never, he was like Olympian god that didn't bother to answer philosophers. He made these jokes about philosophers of physics, and he gives several examples in his lectures of measurements or non-measurements at the quantum level. There's no macroscopic thing at all. And of course, there's no human observing either. And so if you, by definition, talk about human observing, then you're, by definition, bringing in a macroscopic system. But that's not what's key to measurement. What's key to measurement is distinction. Does the interaction make distinctions between the eigenstates in the superposition or not? And that determines type 1 or type 2. And you don't say distinctions to what? In other words, forget about a human being, but distinctions between the eigenstates. Just to take the example, one example I mentioned was the particle scattering off the atoms. And if the atoms all had spins up, say, and when particle scatters off of an atom, it flips the spin, then a distinction has been made as to which one it's scattered off of. So you add their probabilities. If there is no way to tell, in theory, in principle, which atom it's scattered off of, then you add the amplitudes.
And you know, you're getting from point A before the scattering to point B after the scattering. So the question is, do you add the amplitudes of scattering off all those things where there's no distinction made? Or if there is a distinction made, then you've got to add the probabilities. And it all gears down to distinctions. And it has nothing to do with the shifty split between micro and macro and all that. And so, you know, Feynman, and he, you know, gave another example. He said, suppose you have, you know, two particles that collide, and there's two ways in which they can bounce off each other, you know, at a certain angle. And if the particles are distinguished, in other words, they're not identical particles, then you compute the probabilities of each way of reacting to the scattering. If they're the same type of particle, you have to add the amplitudes because there's no matter of fact difference between which one scattered which way.
Can I ask you also a question? Can you hear me, by the way?
Yes.
Yes. So you make the distinction between the discrete version in terms of partitions and the generalized analog, which is pretty good and pretty clear, like going from products to tensor products and so on of the linearized situation. But is there any mathematical formalism to explain that relationship between the discrete version and the linearized versions? I mean, when you drew those tables, for example, is there some kind of a formal mathematical process that takes you from the discrete setting to that linearized setting? Is there some way? I mean, intuitively, it's pretty clear what it is, but can you formalize that in some way?
Would say I'm not. I mean, it's part of the folklore.
Yes.
And Weil uses it obviously in his explanation. And you know, I just, it is what I said it is. You take a basis set.
Right.
What you do to a set, you do that to a basis set and you see what it generates.
Right.
That is pretty exact. There is some cases where you have to make a choice because you may have two things that are generated. And so that's why I called it semi-algorithmic. For example, say you have a numerical attribute. So you have your set U, and your set U is a basis set, and you're given this mapping into the field K. What does that generate? Well, we showed how it generated a linear operator here, but it also generates a linear functional, right?
Yes.
And so which one do you take? And if you take the linear functional, then your inverse image of the functional is a set partition of the vector space that is compatible with the operations of the vector space. So it's not a vector space partition, it's a set partition of the vector space as a set of points where the operation is compatible with the operations. And that type of partition has a special name. It's called a commuting or permutable partition. And that the whole theory of those permutable partitions was developed by the French woman, Dubril, and her husband. And there's a very nice characterization of those types of partitions that was known to Ornstein Orr. Ornstein Orr did a very basic paper on the theory of equivalence relations back in the 1933, I think. And the Dubrils did this earlier work in French. So each way you make that choice, you either get the theory of commuting set partitions of rings or vector spaces or whatever. And Jean Collet was fascinated by that, and that's what he developed. And I no, that's not the right. If you want to do quantum mechanics, you got to take the other fork in the road. Use the numerical attribute to generate a operator like this, and then you get the full, the full set of analogies between the skeletal version
The full dictionary of correspondences.
Yeah. So the end of the paper, I gave the dictionary here, the dictionary for states and the dictionary for observables, as it were. And so, yeah, there may be some cute, nice way to characterize that. I would like to see it. Maybe some of you guys can figure that out. But I'm just sort of pointing it out and saying, it's been used for years. And so very often you have notions of duality, say, that didn't get really characterized until category theory came along. So here's an example of a yoga, a procedure, semi-algorithmic intuitive procedure that everybody seems to know about. But what's the totally rigorous version of it and so forth? It'd be nice.
Thank you.
Are there any other questions? Okay, so let's thank the speaker again. Thank you, David. Always a pleasure. Okay. Fascinating stuff.
My pleasure.
Just what's upcoming next week? Ross Street is speaking, and he's going to speak about the core of a groupoid. Core groupoid does suffice. And the week after is going to be the first time we're going to meet in person. So if you're in New York City and you want to come, so the November 2nd or something like that, 2 weeks from tonight, we're going to meet in person. So please try to come. Anyways, ladies and gentlemen, it's a pleasure. Thank you very much. I'm going to stop the recording.